Hi, my name is Pedro Camargo, and today I will talk about a little experiment I did on my spare time called a model from nothing. Uh, Before we dig into it, however, let's set the expectations for this presentation. This is not about some highly sophisticated ABM DT integration or about the nuances of advanced discrete choice models. The idea here was to build a model for a region for which there is no traditional data sources, such as household travel surveys, government curated networks, land use data, or even census. Oh, and no money for data, software, or labor as well. With that said, the goal here is to build a useful model for planning purposes for a city or region that has most likely never had a model before, and in the process, to develop a workflow or tutorial that could be followed when teaching modeling or taking a first stab at modeling a data poor place. The city I chose to model was Dili, the largest city in Timor-Leste, one of the poorest countries on Earth. It is not a large city, so the modeled area is only about 540 square miles, which is about half of Orange County, California, and just over 500,000 people, so a fairly small city. The network used in the model came from OpenStreetMaps, as all of you would have guessed, but the information on population came from a dataset not often talked about in developed countries, the Facebook Data for Good population layers, which provides separate raster files for several population segments. With no household travel survey, land use information, activity, business information, the only proxy available for activities I could find was the OpenStreetMaps polygon layers, which includes some information on roof covers of buildings and their use. With regards to the demand model, though, that's where I would probably lose the respect of many of you, given the number of rough assumptions I had to make. So I'll keep that part in the interest of time. The network, as I mentioned, came from OpenStreetMaps, but information on speeds and number of lanes was sparse at best. So those had to be asserted by road class, which also came from OpenStreetMaps. In the end, we ended up with roughly 7,400 links and 6,100 nodes. I could have done a lot more to clean the network or look into satellite photos before asserting network data for key parts of the network, but that was way beyond the scope of this project. For zoning, I decided to use hexagons, so I played a little with its parameters to get no hexagon with more than 5,000 people, which was the maximum number I wanted for a single zone. After that, I applied k-means recursively to aggregate those original hexagons in zones ranging from 1,500 to 5,000 people, which resulted in a total of 214 zones, pretty close to my original target of 225. Traffic assignment was also incredibly simple, with all three classes sharing the same network and pure time as cost function. The results seem reasonable on visual inspection, so I'll stop at that. So now it's time to disappoint one of the very kind reviewers to offer comments on this abstract, which is to say that I can't validate the model for a complete lack of data. All I can say is that free flow travel times look reasonable, and that congested travel times are roughly 40% higher than free flow speeds, which is in line with several routes I computed on Google Maps for departure in the middle of the night and during peak times. So that's really all I can do. So after all this, I would be asking if this is relevant at all in practice, or if it is just a silly exercise. There are two arguments for its relevance. First, having something sensible is infinitely better than having nothing at all. And second is not everybody has first world problems, and rough traffic estimates can support countries' bids for road maintenance funds from organizations like the World Bank. It is also valuable to identify critical links in poorly connected networks, especially in the case of natural disaster recovery and access to critical infrastructure such as hospitals. So to make the point that this is indeed a valuable exercise, I wrote a quick 4-step algorithm to evaluate the total demand disconnected in case each link of the network is severed. The results on the map look like a weird traffic assignment plot, but it is quite telling. Some of the results were obvious, like bridges, but others, such as this major roundabout here in the zoom, were quite surprising. And it just goes to show that it's a small piece of the network is disconnected. An entire region of the city might end up being isolated. There's still a lot to do and to discuss, but I'll stop here. Thank you for your attention, and I look forward for your questions and suggestions.